Yes, you can start.
Okay, this is good. Thank you very much. Um, so you can see my screen. You can see today is December 19, and it's getting close to Christmas here. And I want to talk about cluster tilting today. So actually, my goal today is really to wrap up the whole discussion of cluster categories. So the way that cluster categories, cluster algebras can be modeled using representations of quivers. So I want to wrap up the whole subject today, and I will go along a certain way, and then at the end there are some regrets, um, certain things that I did not cover but are still important. So I will inform you just there are these and that theorems that go further, but I am incapable of covering all of that, because then I would like to start with the new topic, which is geometry. So for those who are kind of hanging in the ropes and this whole category is getting difficult, you can relax. I mean, once this is finished, I will start all fresh from new with some nice combinatorics of surfaces and arcs on surfaces. And so this will be all a new start, okay? Good. So today I said I want to talk about cluster tilting. So let me recall where were we yesterday? So uh, we had finally arrived at the definition of the cluster category. So the cluster category for a quiver Q, which is an acyclic quiver, a quiver without oriented cycles like this. For a quiver without oriented cycles, we say the cluster category CQ is defined as a quotient, as a quotient category of something that is called the derived category, and we factor out some relation here. The derived category, we said, can be modeled as an infinite band, and that infinite band contains iterated copies of the category of representations of the quiver. Yeah, so there's a copy of representations of the quiver, there was another copy, a third copy, and so on. I can fill up this band using copies of the category of representations. And there's one operation, this is called a shift. So when I have an object X, I can define X shift 1 here. I just jump to the next copy of the representations. That quiver has another operation, which is the tau translate. Tau translate just moves every point one step to the left. So this X goes to tau X. This is the tau translate. And now in the cluster category, I want to identify these two operations. So if I have an object X and I move one step to the left, tau X, or I do that operation X shift 1, that should be the same. So I have to identify this and that object. This is the quotient we take. So we enlarge the module category a little bit. We go, say, one step to the left. We can also go one step to the right, but we have to identify these two parts. Yeah. So this fits very well with our original result of Fomin and Zeliwinski, uh, the Fomin and Zeliwinski theorem, which told us that, so this is the originally, I announced already, I don't know, on Tuesday or so, the result Fomin-Zeliwinski, that when we have a Dünken quiver, there's a bijection between the set of cluster variables with the set of positive roots of the quiver and the set of negative simple roots. Okay, so the positive roots, they correspond to the indecomposables in representations. So this part here, this is what I always draw in the pictures like that. This is the category of representations. And then we need to give ourselves like n more objects. Yeah, so we have to enlarge it. And this is exactly what happens in that definition of the cluster category. We give ourselves one copy of the category of representations, and then we add n more objects, which are kind of shifted to some sort of negative part. Yeah, I mean, we did this knitting algorithm. If you follow this through, at this point you would get negative indices. So those are kind of negative. So there are n objects which are in bijection with the negative simple roots. So uh, that's kind of a promising start, right? And then we had the big theorem of Burenmarsch, Reinecke, Reiten, Todorov in 2006, that indeed, if we work with that, if we work with that cluster category, then the indecomposable objects are in bijection with the cluster variables, where those shifts of the projectives go to the initial cluster variables, and the rest of them goes to the non-initial cluster variables. And so once we identify the objects, cluster variables with indecomposable objects in the cluster category, we ask ourselves the question, how can we characterize then the clusters? Yeah, clusters are fixed collections of n objects, of n variables. So how can we characterize in this big category which n objects can I pick to so that this corresponds to a cluster? Okay, and the answer is I can pick objects that form what they call a cluster tilting set, and the condition for being cluster tilting set is there are no self-extensions. Yeah, so any two objects that I pick, they should not have an x1. So that was their characterization. And if I take such a cluster tilting object, I take the direct sum of all of them and look at its endomorphism ring. This is then called a cluster tilted algebra. Okay, uh, yesterday we started going more into that topic, but before we go really into cluster tilting, we did a little recurse onto tilting theory, which is a classical precursor of this. Um, so I started with tilting theory. Yeah. By the way, when these cluster algebras, can I tell little stories along the way? Is this okay? About the history of representation theory. So um, I was in 2008. I was in a big conference, the ICRA. This is the largest conference in representation theory. This conference was held in Torun in Poland, and there's a strong group still, and there was a very strong group at the time of people doing representation theory in Torun, and they didn't like this cluster tilting very much. Yeah. They grew up with tilting theory, and then some people come, Burenmarsch, Reinecke, Reiten, Todorov, and they present this cluster tilting, and their motivation was they gave the definition of a cluster algebra, and everybody thought this is terrible. I mean, who likes the definition of a cluster algebra? Yeah, I mean, there's a terrible, complicated procedure. This is very combinatorial. Why would we even deal with that? Why would we consider this? Yeah. So there was some resistance in the beginning, and it took really a while until the community of representation theory, until they made the move from tilting to cluster tilting, until they realized that maybe cluster tilting is a good extension. Maybe there's some advantage of moving away from tilting to cluster tilting. And that took a couple of years, yeah. Then a couple of years later, 2012, 2014, the ICRA was dominated by cluster tilting. Everybody was doing cluster tilting. More than 50% of the talks were about cluster tilting. At this moment, Andrei Skowronski, Ibrahim Assem, and Jose Antonio de la Peña got upset. They said, everybody talks about this subject. I don't like it. And they started their own series of conferences, the ARTA series. And the ARTA in the beginning was specifically designed. There is no cluster talk. You can talk about anything except clusters. Yeah. So that's a bit the background story. Sorry for this. So what did we do? Tilting theory. There's a classical result on tilting theory, where we work also over a quiver, and then a collection of indecomposables. A module is called a tilting module if it has no self-extensions, this time over the quiver Q, and it is maximal with that property, and maximal means we have n indecomposable summons. Such a thing is called a tilting module. And the corresponding endomorphism ring is then called a tilted algebra. So this is the classical theory. I gave you some examples. I hope you got the idea that choosing a tilting module, there are certain rules where we can pick, like in a game, where we can pick certain indecomposables, just always making sure that we avoid certain regions where there would be an extension. So you can pick your things and you find a tilting module. And then we just take the endomorphism ring, and the endomorphism ring would be, we can literally read it off from the quiver like so. The endomorphism ring is this shape, yeah. So that's how we find the tilted algebras. And there was one classical result that tells us that uh, what does it tell us? When we have n minus 1 summons, so we are missing one summon to be maximal, we are missing one summon to be tilting, then theorem of Happel tells us there is always a completion. We can complete it always to a tilting module. And there's how many ways to complete it? There's at most 2 ways to complete it to a tilting module. This is the classical theory. This is good. This is fine. Every partial tilting can be completed to a tilting module. However, from the cluster perspective, this raises a problem. There's an issue here. Namely, what if we have only one completion possible? And we considered one such example, say we have 1, 2, 3, 4, 5 indecomposables in a quiver of type A5. This is the good number. They form a tilting module. But if I want to mutate T4, then I see there's no space left. I cannot put this anywhere here nor here, and this region was already forbidden. There's no space left in the category of representations. I cannot replace it by anybody else. So if I would look at these 4 summons and I want to replace it, there's only one completion possible. This is bad news for cluster tilting because we would like to consider these 5 and define a mutation. So we want to remove T4 and replace it by somebody different. That's a clear mutation, right? But it's not possible in terms of tilting theory. There is nobody else that forms a tilting module. So tilting is not good enough to model mutations. This is the shortcoming of tilting theory. And coming from cluster tilting, we want to mutate. Every cluster variable can be mutated. So this is not good enough. Let's therefore look into the larger category, the cluster category CQ, where we added a few more objects and we give ourselves more space. And that more space makes it possible that we can mutate. So cluster tilting. The theorem by Buren, Marsh, Reinecke, Reitentotteroff in 2006 for Dynkin quivers is the following. I have a Dynkin quiver Q with n vertices, and then I consider a cluster tilting object given by n indecomposable summons, non-isomorphic, an object in the cluster category CQ, so there's no extensions between them. And then for any index k that you choose between 1 and n, there exists precisely one object tk prime in the cluster category, such that this object is different, is non-isomorphic to the tk, which was already sitting here. That means I can replace it. Yeah, that means I can define a mutation of t by take out the object tk and add this other different object tk prime. And this new thing is again then a cluster tilting object. So I can always mutate. Mutation is always possible. That's the big result that shows that or the combinatorics of those cluster tilting objects really models the combinatorics of clusters and their mutations. And under the bijection of Fomin-Zelinsky, this mutation is compatible with the mutation of cluster variables. So if the cluster tilting ZT corresponds to some cluster U, and I mutate the cluster by replacing cluster variable UK by cluster variable UK prime, I do get the same thing if I perform the mutation here, and then I find a new variable corresponding to this TK prime. This will be exactly the UK prime. So these two processes work together very well. Yeah. The cluster category with the mutation of cluster tilting objects is really a nice model for the combinatorics of cluster algebras. And the people say now the cluster algebra is, the cluster category is a categorification of the cluster algebra. Yeah. We model using objects in a category the combinatorics of cluster variables. Now, let me talk a few minutes about the cluster tilted algebra. This is the endomorphism ring of T, now in this larger category. So all morphisms between the summands of T in the larger category, the cluster category, let's denote this by B tilde. And a theorem of Burenmarsch-Reiten in 2007 says that, again, I want to look at the functor hom T, now this time defined on the cluster category, and I would like to use this to compare the cluster category with the modules over this cluster tilted algebra B tilde. So hom T defines me a functor from left to right, and in fact these two categories are almost equal, I would like to say. They are equal up to n indecomposable objects. Namely, when I factor out the object T, when I delete the n summons belonging to T, then this quotient is isomorphic to the module category of B tilde. So all those cluster tilted algebras are very closely related. They all have the same number of indecomposables, even if it's infinitely many. Yeah. And the difference between the module category and the cluster category is only by n indecomposables. So they are really very closely related. And this is different to classical tilting theory. Yeah, in classical tilting theory, that could be finite and the original algebra could be infinite or the other way around. Yeah. Okay. And then I wanted to run through. Do you have questions so far? Let's start from here. Questions, concerns, remarks, stories. No, it's good. Okay. So I would like to basically go through the same example that we did yesterday for the tilting object. The tilting object was computed in here, and now I enlarge it by these two pieces, which I identify. I'm now in the cluster category. Okay, so if you want to find cluster tilting objects, you do the same game. You choose some point, and then you have to understand where are the morphisms. The morphisms are still formed by those rectangles in that region in the cluster category. There's a non-zero morphism, and all the rest does not get any morphism. This works completely in the same way. If I now want to understand what are the morphisms from some summand into tau of the other summand, then I simply shift that ranked rectangle one to the left. So that summand maps non-trivially to this triangle, this rectangle here. So I can control really where there are non-zero extensions, where there is some non-zero element from that one into the tau shift of somebody else. I play the same game as I did yesterday in tau in tilting theory. Just this time my category is a little bit larger. That's all. That's the whole difference. That's the whole difference. Yeah. So yesterday we were looking at this example of a of a tilting module given by
I'm
summons.
sorry.
Yes?
Yeah, yeah. Can you go back to the equivalence of those two categories?
Yes, sure.
Yeah, you need like CQ mod T. T is just a tilting object. Like you need a category, like at T or something.
I don't formally factor out just one object. I factor out the additive category generated by this object. Yes, so I take all direct summons of this one. Yes, thank you very much.
I see. Which you
Or
call at.
formally, I mean, what is a quotient of a category? This is like I need an ideal. I factor by an ideal. So I factor by the ideal of all morphisms that go through T or something like this. Yeah. But on in terms of indecomposables, I really delete T.
I see.
Yeah.
Yeah. Thank you.
So let's say add. You're more comfortable if I write add T here.
Yes.
Yeah. Okay, that's good. That's good. Thank you. So in terms of our example that we considered yesterday, there were the 1, 2, 3, 4, 5 blue dots. These are 5 indecomposables. Uh, they are compatible with each other, meaning there's no X1 between them. For if I work in the category of representations or if I work in the larger category, this is true in both cases. So they also form a cluster tilting object. I consider this one, yeah. You can check this by hand if you wish. And so what is this time around? So let's go into this. What is the cluster tilted algebra B tilde this time around? Yeah. So I look for morphisms. There's a morphism from T4 to T5. This gives me that arrow here. From T1 to T5, that gives me the arrow here. Then from T2 to T1, from T1 to T3, this gives me these two arrows. You see what I'm doing? Yeah. Now things start getting a little bit more interesting. The tilted algebra had nothing here. In the tilted algebra, there was no arrow here. Yeah, because if I go from here to there are zero relations. There is no morphism from T2 to T3 inside the category of representations. Okay, good. But now look carefully. If I start in T3, then I can go along that arrow. I can go along that arrow. Arrows are morphisms. They're irreducible morphisms. But this guy, look, we identified with the guy over here, didn't we? So I can continue going down here and going down here, and I reach T2. So there is, in fact, a morphism from T3 to T2. You see that? In our new category. So the new larger algebra has one more additional arrow from 3 to 2. Okay, so this is an algebra which is slightly larger than the tilted algebra, because now we enlarge the category, we have the possibility to have more morphisms. Okay, and I do have zero relations between these morphisms. If I compose any two of them, I will always get zero. Okay, so that's really the cluster tilted algebra. That's okay. This is okay so far. And so that's let's do this. Let's apply the result that the cluster category, if we mod out add T, if we mod out add T, then we do get a category which is equivalent to the category of B tilde modules. So what do I do here? I'm in my category, in the cluster category, and I simply delete everybody. I delete these 5 vertices and all the morphisms attached to them. Yeah. And if I do that carefully, then you obtain this category. So now there are some kind of holes. Yeah, I give you the ghosts of where the TIs were sitting before, but the category is really given by the black part. So this is the category. You still identify this part with that part. This is the category of modules over that algebra B tilde. Okay, and you do see that taking out, I mean removing such a summand Ti creates over the cluster tilde algebra B tilde creates an injective here because this is an object that has no tau translate, has no tau inverse, yeah, and it creates a projective because this is an object that has no predecessor under tau. If I take out T1, yeah, this creates a hole, so this creates to the left an injective and to the right a projective, yeah. So I see the indecomposable projective B tilde modules sitting always to the left and to the right of the holes. Do you see a little bit what I'm doing here? And then I need to knit it together. And if I want to knit it together, okay, this is already done. I just copy from what I had in the cluster category. This is already there. Yeah. So that kind of gives a nice way to quickly compute the Arnold quiver of such a cluster tilde algebra. Okay, that's good. And now, last remark. What about the mutation now? Yeah, I mean, we said before that as a tilting object, I cannot mutate this T4 because there was no space. So let's consider now the cluster tilting situation. Here was my object T5. I want to replace it by somebody, and you can verify I cannot replace it by anybody here nor there because this was not possible in the tilting case already. But I create some new place, I can move it over here, yeah? And that is a valid object. You verify this has no self-extensions with the rest. So this is the T5 prime. My mutation is now T5 is replaced by T5 prime. I do find another complement of this for people here. And if I do that, if I apply that mutation, what is the mutated cluster tilted algebra? I flip from 5 to 5 prime. So where there was an arrow from 4 to 5 before, there's an arrow from 5 to 4 for prime now. So I basically, do you see what I'm doing? This is a reflection. I flip the orientation of that arrow. Instead of arrow 4 or 5, I have an arrow from 5 to 4. Yeah. So that's kind of what a reflection is doing. Okay, good. I give you a little moment to think about that. Do you have any questions? Give me 1 second. I'm getting hot here. Okay, good.
Yeah.
Yeah.
So what is the abstract definition of a cluster tilted algebra? Just like you had one for tilted algebra, or is this the like this recipe is the definition?
The tilted algebra is the endomorphism ring of a tilting module. The cluster tilted algebra is the endomorphism ring in the cluster category of a cluster tilting module.
Okay. Okay.
You just add a cluster, the word cluster everywhere. These are just endomorphism ring of cluster tilting modules.
And how much of this theory holds for bound quivers?
Our whole definition of the
Yeah, you are assuming Dinkin diagrams for a lot of lot of results.
Where's my cluster category? The cluster category, the definition of a cluster category like so can be given for any quiver that has no oriented cycles.
Okay.
So a quiver with, if I have an oriented cycle, then the path algebra would be infinite dimensional. We don't do that, yeah. But if I have a quiver without oriented cycles, I can define this cluster category, and this notion of cluster tilting works all fine. Yeah, in that generality. Here the quiver need not be a drinking quiver.
Okay.
Yeah.
Okay.
If I want to go away from the hereditary situation, if I want to go away from quivers to bound quivers, things become more complicated. You can define, when you have an algebra of global dimension 2, at most 2, you can define something, you can define a cluster category. This has been done by Claire Amiot. And this has some general some properties which is now known as a two-Calabi-Yau category. And in that context, you can still consider cluster tilting and mutations.
Okay. Okay. Thanks.
I have a question. So,
Mm-hmm.
like you considered that B tilde, cluster tilted algebra.
Mm-hmm.
So, if you just consider the tilted algebra, do we get some sort of embedding or something into the cluster tilted algebra?
Yes.
Okay.
Because they are defined as the endomorphism ring. So the tilted algebra is the endomorphism ring in the category of representations, and the cluster tilted algebra is the endomorphism ring in this larger category. But since the category of representations is contained in the cluster category, so if you have an object T that is defined, that is sitting inside the representations, you can view the same object here. You can compute the endomorphism ring. You can compute the endomorphism ring in over Q of T, and you can compute the endomorphism ring over this larger category, CQ of the same object. And in general, this is going to be larger than this one. Yeah, that is a little bit what we saw for B tilde here. There was this one additional morphism that you only can realize in the cluster category, and which was not present if you're just working in the category of representations. Yeah, so in that case, B, the tilted algebra, B, the tilted algebra, would be given by the same thing. However, we have not this last arrow. So that would be the tilted algebra, B. Okay, so it is smaller, and you can control in general your, so there's a theorem that says that B tilde is a trivial extension of B by the bimodule X2. I forgot that. Something like Q and the dual of Q, something like that. I should know it because I'm one of the authors, so this is a joint paper with Ibrahim Assem. myself and Ralf Schiffler. The cluster tilted algebras are trivial extensions of tilted algebras given by some bimodule made of X2. Okay? Was this your question?
Yes, yes.
Okay, good. Thank you very much. Okay, good. So this is more or less the part that I really wanted to cover, and then I come. Then here are my regrets, results that were not covered in what we did today. But I want to really wrap up this cluster category story, and so tomorrow I can continue talking about geometry surfaces. Okay. So there's one result. So there's one question that you might want to continue. We showed that when I want to mutate, so say I'm given a cluster tilting object, a set of indecomposables which form a cluster tilting object, and I want to mutate in K. I want to remove the summand Tk and replace it by a new summand Tk prime. Yeah. And in the examples, we say, okay, there's not much space. If I want to remove this one, there's no space. I cannot put it here and not here and not here. And there's the only place possible. I have to put it here. But is there a better way to describe this Tk prime? Yeah. Is there an actual formula or something like that? And indeed, there is a formula. And maybe if Isha was talking about tau tilting yesterday, you were doing something like that. But there's a way to define, there's a way to construct the mutated summoned Tk prime in the category, in the cluster category, and this goes as follows. So there's a theorem which was for Dynkin quivers already in the original paper by Buan, Marsh, Reinecke, Reiten, Todorov. And then in a more general version, it has been stated by Iyama and Yoshino, and they stated in the more general context of two Calabi-Yau categories. This is what I was just saying to Amit. This cluster category has certain symmetry properties. There's a shift between xi and x2 minus I. This is a two Calabi-Yau category. And in that general context, it can be shown that when I have a cluster tilting object, which is made from summands T1 up to Tn, when I have a cluster tilting object in that category or in this category, then I use the fact that those are triangulated categories. And I wanted to avoid that notion. I didn't want to start defining what is a triangulated category. In general, this is a bit lengthy process if I want to give the axiomatic approach to triangulated categories. But they okay, so what is this about? They work in that context, they work with this full machinery of triangulated categories. So if we just accept that this exists, there's some additional structure. For cluster, for tau tilting, this would be more short exact sequences. Here, this role is played by triangles. Okay, so what do we do? Suppose we are given T with n non-isomorphic summands, and suppose we want to replace Tk, the k summand, by some other summand. Okay, so we take it out. That means let's remove from T that summand Tk, and let's look at the additive category generated by this. So let's look at all direct sums of objects that you can form from T, but not this one, not Tk. Then Tk itself is not in here because we just removed it. Yeah. What we do then is, in general, when you have some object, in a category, some object tk in some category, and you have some subcategory at t minus tk, and t does not necessarily belong to this, so there's a subcategory which is kind of somewhere else. There is a notion of approximation, so there's a closest object t prime that belongs to this subcategory, and there's a morphism into that t prime. Yeah, so this is approximation theory. Under some reasonable assumptions, when you fix one object and you have a smaller subcategory where this object does not belong to, there is still one closest approximation of tk into this subcategory, and this closest approximation is called t prime. So far, so good? Yeah. Isha, this is more or less, that's correct. And so this approximation is given, there's a morphism from tk to t prime, and it satisfies some universal property. Whenever I have a morphism from tk into that subcategory, every such morphism would factor through this U. So this is a universal property. This guarantees unicity. It's unique, okay, up to isomorphism. And I take this thing. This can be constructed. And now, when I'm in a triangulated category, by some magic, I can always complete this to a triangle. That's the part I cannot really explain you. This is one of the axioms of a triangulated category. I can complete that morphism into another object tk prime here, and this embeds then into the shift of this object I started with. This exists in a triangulated category. Yeah. And it's called the cone of this morphism. So you define in that general context of a cluster category or a two-Calabi-Yau category the mutated summon tk prime to be the cone of the approximation of tk in the remaining part of t. That's the construction. This is how you mutate, like so. That's okay? Or not okay. You see there, you use some machinery of triangulated categories, which I did not explain. But that's how it works. Isha, did you discuss something like this for tau tilting?
I discussed it for tilting. Like, I mean, if it exists, then it would be kernel of some approximation or the co-kernel, depending on which direction you go to. But yeah, I discussed it for tilting, yes.
Okay, so it works for tilting,
Yeah.
and in the general context of two Calabi-Yau categories, you just construct a triangle which is given by the approximation, and then you take this guy. That's what it is, right?
Yeah.
Okay, good. If
I
you
mean,
have
just
no,
to, I mean, if for people who are not comfortable with triangles, like they can imagine short exact sequences, like short exact
yeah,
sequences will be examples of triangles, but not the other way around. But yeah.
yes. If
Yeah.
you, yeah, if you don't like triangles, think of kernels and co-kernels. So you can complete this to some object here. Yeah, this kind of a co-kernel. Okay. But you see a little bit why I did not want to go into the details of this, because I did not want to define what is a triangulated category. Yeah. Some more things. Yeah. Okay, let's do this. I mean, we have this bijection between indecomposable objects in the cluster category and cluster variables. Yeah. So we know the every object in the cluster category corresponds to exactly one cluster variable, and the objects in the cluster category, if they come from the part where we have, so either they are shifts of the projectives, then we know them, they correspond to the initial cluster variables, and for the rest of them, the other objects in the cluster category, these are called, I call them V here. They are some indecomposable representations. So if you just give me an indecomposable representation V, can you tell me what is the corresponding cluster variable? And I want to say, without going through all the knitting algorithm, I mean, of course, I could start the knitting from the beginning and I knit forever until I find at the same place the cluster variable and the object, then I know these two correspond. But can I do that by all means? Can I do that without going through the knitting procedure, starting from the initial variables? Is there a direct formula? Yeah, so directly give me V, what is the cluster variable? That's good. That's a good question. Yeah. And it has an answer. This is the Calderot-Chaponton formula. So given an indecomposable representation, what is the corresponding cluster variable? CCV. It is given by this formula. Do you see this formula? Okay. So yeah. So this formula is a bit complicated, as you see. Let me just introduce V has a dimension vector. So this is the pointwise dimensions of this representation. Let's call them D1 up to Dn. Okay. Then how do I compute the cluster variable, which is the one which corresponds under this bijection to the indecomposable representation V? The cluster variable is going to be a Laurent polynomial. So this is going to be some polynomial divided by a monomial. Okay, the monomial you see here, yeah, we divide by the initial variables to the powers di, the dimensions. This is what we said from the very beginning. This has to be, okay. We knew that already. The question is, what do you write in the numerator? Yeah, we must find the polynomial in the initial variables, which is placed up here. And the answer is written here. Okay, so let me go through this in a little more detail. You see that it is a polynomial. I mean, it is a sum of products of the xi's. So this is a polynomial in the initial cluster variables. Xi is to some exponent. Okay, it's a polynomial in the cluster variables. You see that. So where do you want me to start? Let's first go for the no. So the sum goes over all dimension vectors which are smaller than the given dimension vector D. Yeah. There's only finitely many of them because the dimension vector D, these are some natural numbers, and there's only finitely many vectors of positive integers which are smaller than this one. And I take the sum over all those possibilities. In general, this is a large sum, yeah? So for any dimension vector E, which is smaller than the dimension vector D, sorry, I call this D here, yeah? So when I have an E which is smaller than D, just pointwise, coordinate by coordinate, I have numbers that are smaller equal to Di. When I have such a thing, first I form the Grassmannian, the Grassmannian of all submodules of this dimension vector E, which are submodules of V. Okay, so this is a little bit of geometry. We consider the Grassmannian of planes in n plus 3-dimensional space. I can also consider the variety of all representations of dimension vector E sitting in the representation of dimension D, sitting in V. So there's in general can be infinitely many such submodules of a fixed dimension. And those infinitely many submodules, they will form an algebraic variety. And the algebraic variety can be measured by the Euler characteristic. The Euler characteristic will compute a number out of this algebraic variety. And this is the coefficient that I take here. So you see why I didn't go into the details of this formula, because it's kind of complicated. So this is the Euler characteristic. This is the Euler characteristic. If I have only one or only finitely many submodules of dimension E, then the Euler characteristic is 1. Forget about this. But in general, the variety of submodules might form an infinite set. It might form something like a P1, and then the Euler characteristic is something different from 1. Okay? Good. And the exponents of my initial variables, okay, there's a formula. I mean, we sum up over all arrows that end in I and multiply it by this number EI in the dimension vector, and we do the similar thing for arrows that start in I. So these are the exponents that you get, and you obtain a polynomial, and really writing the cluster variable corresponding to V as a low-row polynomial satisfies this formula. Okay, very good. Do you have any questions on this?
So like when like Born, Marsh and Marsh, Reinecke, Reiten and Todorov gave the proof, they did not give an explicit bijection. They just showed that starting with the initial cluster variables and the knitting process, you can get all of them. Okay.
I would need to go back to the paper, but as far as I remember, they showed just that the process of mutation, the knitting procedure is compatible. So you start with either set,
Yeah.
and you
obtain everything.
you move along, so you get a bijection. So you get a bijection kind of, you show by recursion on the knitting process that you have a bijection.
Okay. I see.
But
Thank you.
they did not answer this question. So give me an indecomposable, what's the corresponding cluster variable? I mean, this is it's a good question, right? I mean,
Yeah.
what is it? Okay, Calderon-Chaponton gave the formula, but it's a kind of a disappointing answer. It's really complicated, right? Yes. And unfortunately, these Euler characteristics, they can be negative. So there are some algebraic varieties whose Euler characteristic, this is an alternating sum of certain dimensions, but it's an alternating sum. So it can be in the sum, it's a negative number. So just this formula does not prove the positivity conjecture. Yeah. The coefficients you find here, they could be negative in general. So that does not, it's a formula, but it does not bring us closer to the positivity conjecture. That's what it is. Okay. Good. Are there more things that I wanted to? Yeah. Okay, there are some more things. Okay, let's move on. This is an old version. This is a result by Dirksen, Weimann, and Seliwinski, 2009. That was a result that was a precursor to tau tilting theory. I did not talk about tau tilting theory. Yeah. But what we see in our cluster category is that we always have a representation and then some projective objects. So they decided to consider such pairs which are made of a representation and a projective object, so a certain sum of indecomposable projectives, and they consider those pairs and they call it a decorated representation of the quiver Q. The representation is decorated by this additional information of the sum of projectives. If you discuss tau tilting, this is very close to it. You see what I mean? Yeah, I mean, as a support tau tilting pair, you can basically write in this way. Yeah.
Yes. Yeah, I didn't talk about pairs because
Yeah.
I didn't want to introduce pairs of projectors, but yeah.
But there is a version of the story which looks exactly like this. Yeah. So this is kind of a precursor to tau tilting theory. When was tau tilting theory done?
2012, I think. Like the paper by Adachi, and Wrighton.
Yeah, so this was
Yeah.
3 years earlier.
Yeah.
No, but it's kind of natural if you look at the cluster category that you consider pairs a representation and some projectives. That makes sense. So they considered this one, and then one of my original yeah. So where did I start? So I am here. One of my original motivations for this week, Monday, was that we defined reflections when we have a sink or a source. But what shall we do? Is there some kind of a reflection at a vertex K which is not a sink or a source, right? So that was my kind of original motivation. Why would we define that cluster mutation to start with? Yeah. And the result is that we need to introduce, or we motivated that we need to introduce some additional error from I to J, and then we turn around the orientation of the arrows. So that was our mutation at an arbitrary vertex, which is not necessarily a sink or a source. Yeah. Okay, good. In the classical theory, if we mutate at a sink or a source, we have the reflection functors. Yeah. Is there a kind of a reflection or a mutation functor for mutation at such a vertex? That's a reasonable question. Yes. What happens if we reflect, if we mutate? Is there such a nice functor that can be described in terms of linear algebra of the representations? What do we replace that vector space with? Yeah, and what are the maps? What are those maps attached to it? Okay, good. So this is my question, you understand? So Jackson, Wyman, and Zeliwinski studied that question in 2009, and they studied that question in the context of, decorated representation. We enlarged the representation by some additional data, these projectives. And then they defined a reflection functor or a mutation functor which acts at an arbitrary vertex K, need not be a sink or a source. Okay, so there's a formula really. And the formula is here. Good. Okay. Good. Do you see my formula? And maybe we start a little bit. Okay. Let me explain this a little bit. Suppose we would like to reflect at a sink. Okay. So suppose we were at the situation where K is a sink. Let me write this in another color. Suppose we want to apply a reflection at a sink K. You did reflections in week 1. Yeah? Do you remember what we were doing? We kind of look at all the maps that go into K. Yeah, I mean there's a bunch of arrows going into K. So we do have a vector space at position K, and we have a bunch of vector spaces mi1, mi2 up to mi something that go into K. We want to take all them together. So we want to take the direct sum of all those mij's, and this is what they call m in yeah, the vector space of all the direct predecessors of K. They call this M in K. Everything that goes into K, I take the direct sum of everybody here. And we collect the linear maps that I have given in the representation into one matrix, which I write here. And this one matrix, they call it alpha K. Yeah, that's okay. This is how we defined. No, this is how we started. Then what is the reflection? I mean, you want to reflect in the vertex K, so you want to reverse all arrows adjacent to K. So you're looking to replace this by a K prime, which now goes into all the predecessors of K. So what we want to do is we want to find somebody here that maps into that sum. And what do we take? We just take the kernel of this map, because this is how we can, I mean, if you give me any map and I want to look for somebody here, I would tell you, take the kernel. Yeah, I mean, there's not too many choices otherwise. And that is the reflection. Yeah, I mean, the reflection, when we have a sink, then the reflection functor did you call this SK or SK plus or SK minus or something? Do you remember?
It was plus.
Thank you very much. The reflection functor was called SK plus of M, and the value of SK plus of M at this new vertex was exactly that kernel. That's okay? This is what has been done in week 1, right? Okay, good. Now our the situation is a bit more complicated, because K is no longer a sink or a source. There's some other arrows around. There's some arrows that go in, and there's some arrows that go out, and there's possibly some arrows between those arrows that go in and that go out. Yeah, that's the general situation, and we still want to define we still want to define new vector spaces, which in that paper by Jackson, Weimann, Zelewinsky, they denote them by M bar K, and they put some, so they want to define a mutation. So MK should be going to M bar K. And how do they compute M bar K? Good. Here's the formula. This is how you compute the new vector space at the vertex K after you mutate it at K. Okay, so there's a good news. You still see the kernel, yeah? And if nobody, sorry, if you still take this kernel. If those here were not there, then there would be nothing here and nothing there. So it is still the kernel if it's a reflection at a sink. Yeah, if it's not reflection at a sink, you need to pay a price, and you need to fill in some more vector spaces. And what you need to fill in is this guy, and it looks a bit terrible. I'm sorry for that. Yeah. So you take the kernel of the ingoing maps, and the kernel of this diagonal map, and you divide it by the image of the outgoing map, and blah blah blah. This is what you do. This is the reflection functor. If you were reflecting at a vertex which is not a sink and not a source. Yeah. And good. This looks fairly complicated. Do you agree? But it can be done. I mean, it's all linear algebra. It's kernel and images of linear maps. It can be done. Okay. However, this is not the most elegant way of doing things, and I would maybe prefer to use tilting theory instead, yeah. And then I go into the direction of tau tilting theory. So if we have a source, in the quiver Q, then in the Ausländerreiten quiver we would see that the projective at Q would be mapping into some other projectives, and those itself are predecessors of the tau shift of that projective, and tilting would be the following. So I would define a tilting module T as taking all the projectives different from K and replace PK by the projective at K by its tau inverse. So I replace this one by that one. I move this over here, yeah? And if I look at the endomorphism ring, what happens when arrows go out here afterwards? Oh God, my arrows are really wrong today. I'm sorry. Under this tilting process, I replace outgoing arrows by incoming arrows. I flip the orientation of the arrows adjacent to K. That's really what it is. Yeah, and so this reflection functor is really of the form hom T blank, where T is a tilting object, and it is a functor from representations of Q to representations of the reflected quiver of Q. This is how you can model those reflection functors using tilting theory. And then I would just, in the general situation, do the same thing, take a cluster tilting module and model the reflection functor as using hom T blank. This is the better approach, I think. Yeah, it's not as explicit. You need to compute homomorphisms from the tilting module, but this can be done easily if you know your category. And I think it's still easier than computing those things. Yeah. Okay, so this is good. Where are we? Okay, we are here. Okay, good. We have like, what, 20 minutes left? So this is all what I wanted to tell you on cluster tilting theory, what I wanted to tell you on, yeah, cluster categories. Okay, and now I'm ready to start with geometry. Do you wish me to start slowly with the geometric part, like a 15 minutes? And then we can continue today, or shall I not do this in the last 20 minutes? What do you think?
Please continue.
Okay, good. So we start new topic. Yep. It's not completely new topic because it's still cluster algebras. There's a nice model by Fomin, Shapiro, Thurston, where they in 2008 they showed they constructed a cluster algebra from the datum of a surface. Good. So I slowly want to talk about now the geometric model part. So this is part 2 of my lectures, gentle algebras and geometric models. So I will start with the geometry. Okay. So the first part of this is what is called marked surfaces. So we need to go through that a little bit. What is a marked surface? And please, we start new. Please feel free to interrupt me. Please feel free to ask questions when I shall explain more details. Okay. So we start with an oriented compact surface S. An oriented compact surface S. A I have surfaces in topology up to isomorphism, they are up to homeomorphism, they are classified by their genus. So there are surfaces of genus 0. This is just a sphere, yeah. I want my surface to be compact, so I do not consider the plane because this would be unbounded. Yeah, I really want compact surfaces, and up to isomorphism, the only compact surface of genus zeros is the sphere. I have a surface of genus 1. This is the torus. You see this picture, the torus. You know what I'm drawing here. It's the surface that you see. And then the genus can increase slowly. A surface of genus 3 would be such a thing. This is like a torus that has got 2 holes. So I mean, I can go through here and come out on the other side. And early in the classification of oriented compact surfaces, they are given by their genus. That's okay? Good. I am currently in Germany and I can eat for breakfast a surface of genus 3. You see it here. This one, this is a wonderful, perfect example. I mean, the surface of my pretzel is really a surface of genus 3. There's 3 holes. You can see them here, right? And so these are nice examples. You agree? Good. And okay, so fine. You're okay with this? There are non-orientable surfaces, the Klein bottle, but I'm not going into this. I want it's essential that my surface is oriented. Okay? Good. Okay, questions? No, you're good. Okay, fine. Then I gave you some picture here. This is a surface of genus 2. And you see, I do more things. I will cut out certain disks here, and then I will decorate these, the boundaries that I create here by some points. So that's what will be called a marked surface. Okay, so let's do this slowly. From my given surface S, I will cut out a finite number of disjoint disks, like so, 1, 2 disks. Okay, if I cut them out, then I will create a boundary. I mean, the where I cut out the disk, now there's some boundary. Before, the surface had no boundary. I mean, this was closed. Okay, now I create a boundary component here. This is one circle. I create another boundary component here. This is another circle. So cutting out a number of disjoint disks from a surface creates a boundary denoted delta S, and the boundary is a disjoint unit of cycles. Yeah. Now such a thing I call a surface with boundary. A surface with boundary is a surface where I cut out disjoint disks. That's good so far. Okay. And we finally come to the definition. What is a marked surface? This is the basic object that we will consider from now on. A marked surface is a pair of a surface S and a finite set M, where this S is a surface with boundary, so a closed surface, but then I cut out some disks. And M is a finite set of so-called marked points, and I want them to be all sitting on the boundary. Yeah. So my the points in M are here denoted in black. 1, 2, 3, 4, 5, 6. There is a version of marked surfaces where they do allow marked points also in here. These are called punctures. But for what I'm doing, I do not want any punctures, so I do not allow punctures. I have kind of an unpunctured marked surface. That's okay? Good. And we make some further assumptions to avoid certain problems, I first insist that every boundary component has at least one marked point. Yeah, so on that boundary component, at least one marked point must be sitting there. And I avoid certain small cases because later I want to talk about triangulations. And there are certain small cases when I would have just a disk, when my surface would be given by just a disk and only one point, then I could not find a triangulation of that surface. So in that particular case, I want to have at least 4 mark points. That's all. Good. Examples. So let's start with examples of genus 0. That means I have a sphere, and then on this sphere, I want to take out, I want to cut out one disk, like so. So I cut out the disk, and then the sphere where I cut out the disk, you allow me to consider my surfaces up to homeomorphism. So I want to flatten it out. I pull everything down here, then I get an actual polygon. You see what I do? Yeah, so I have my, ouch, I have my sphere, I cut out the disk there, and I flatten everything down to the plane, and then I find just a polygon. I find a polygon, and the marked points are the points on the polygon. I have a disk with m points, yeah? That's good. By the way, my drawing here is really, really complicated. I mean, when I draw a sphere, how would you normally draw a sphere? Yes, you would draw a sphere, say like how would you draw a sphere? This one is a sphere, like so. Is this a sphere? Or sometimes we do like we indicate the equator here. That one is a sphere, right? That's very good for our intuition. However, none of these lines is an actual line that is relevant. Yeah, I mean that the outer line here kind of gives me the outer shape of a ball, yeah, but it's not actually an actual line on the sphere. And this one is not, this is just for intuition. The equator, I do not want to specify either. So uh, anyway, you see my problem. This is kind of complicated to these drawings, yeah. If I pull everything down here on the plane, then I have an honest polygon. And now the polygon is filled, right? I mean, this is now inside. I turn outside versus inside. I have a polygon. If I have a sphere and I cut out 2 disks, one here and one there. Okay, now it depends up to you. So either I can say this is an annulus which has an inside and an outside, yeah. So I consider all that region. This one here corresponds to the region here. This is an annulus, yeah. Or if you prefer, you can draw it. You can draw it like a cylinder. I mean, if I take the sphere and I cut out the disk on top and on bottom, then I would get something that looks like this, a cylinder, yeah? The cylinder where I had, I cut out up on the top and the bottom, I cut out 2 disks, then I get this one. That's okay? So on the cylinder, I can have some marked points on the top and on the bottom. Or I draw it as an annulus, like everything in the plane, as you wish. Yeah. So we need to slowly develop a good intuition how to draw these examples because we will deal a lot with those things. Okay. Now, yeah, I was talking about curves in the surface or arcs in the surface. So this is the next notion that we really need to discuss. So we call an arc in the surface. So SM is as a bounded marked surface. An arc is a curve gamma that lives in the surface such that the endpoints of the curves are marked points. So I can go from here to here. I can go between two marked points. I could go from here around to this marked point. I can go from here a million times around and then I end in that marked point. All these are good arcs as long as they do not intersect themselves. Yeah. So something starting here and intersecting itself and going back there is not an arc. This is not allowed. Okay. I do not want my arcs to intersect themselves, except maybe, do you call this an intersection? I mean, I can have an arc that starts here and comes back to the same point on the boundary. This is allowed. Yeah, so gamma does not intersect itself, except maybe on the endpoints, okay? Further condition on an arc gamma is that it intersects the boundary only in its endpoints. Yeah, so I do not want an arc starting here, passing through that point and then going there. This is not one arc. Yeah, that for me would be two arcs, this one and that one. Okay, and furthermore, gamma should not be contractible. This thing here is not an arc, because that I can contract it just to the point here, and that's not an arc for me. So gamma does not cut out a monogon, so such a thing. Yeah. Okay, so such curves satisfying these four conditions I call an arc. That's good. Okay.
Sorry, yeah. So, do you want gamma to be just continuous or also smooth?
Excuse me? Sorry, I didn't get you.
Yeah. Do you want to assume that gamma is continuous or also smooth?
Let's say let's say continuous.
Okay, okay.
Let's say continuous. So to be really honest, I would like allow myself the possibility to draw the
You mean broken lines? Yeah.
I would like to draw the circle with three marked points. I would like to be able to draw it like so.
Okay. Thank
But
you.
in general, my curves can make those moves. Yeah, I mean, I don't want them to be smooth.
Okay.
This is all. Anyway, I will come back to this later. I will consider arcs up to homotopy, so I can move, I can bend my arcs in any form I wish. Yeah, it just need to be continuous. So when I say curve, then I should add a continuous. So curve is just a map from the interval 0, 1 into S, and it should be a continuous map, but I don't ask anymore. Like so, that's okay?
There's a
Yes,
question
yes.
in the chat. Yeah, please explain the last property, monogon property, once again.
Yes, this is very good. So a monogon. So I could a priori think that I have some boundary here, and there's a point M in the boundary, and I could a priori allow myself to consider a curve gamma that looks like this. Yeah. However, if there is nothing in the interior of gamma, then that if I fill this interior, that would be called a monogon. Yeah, so that shape here, that's a monogon, a polygon with one point. Yeah, so that's a monogon. And in that case, gamma, the curve, would be homeotropic to just the point. I can shrink it. I can contract gamma. I can contract gamma to be smaller and smaller and smaller until gamma is just that point. And if gamma is just a point, then I do not consider it as an arc. That's all. Yeah. There's another case which is similar to this. What happens if I consider a curve gamma that goes between 2 points on the boundary? So there's the boundary and there's gamma, and gamma can be moved to the boundary. So I can move gamma continuously to here. This means gamma cuts out a diagon, a polygon with two vertices. Yeah. And this is allowed. So cutting out a monogon is not allowed, but cutting out a diagon is allowed. However, this is still a special case. Such an arc is called a boundary arc. Yeah, so I could equally well draw gamma here. That would be the same thing. Yeah. And so I subdivide my set of arcs into two sets, boundary arcs and internal arcs. Internal arcs are the ones which are not boundary arcs. Yeah. Otherwise, gamma, if it's not boundary, it's called an internal arc. Yeah. And big remark, in everything I do, I consider my arcs up to homotopy. That is, when I have two such arcs, two such curves that go from the same boundary point to the same boundary point, and there's a homotopy that can continuously transform gamma into gamma prime, then I consider them equal. This is one arc. So I consider my arcs as homotopy classes of arcs to be really strict. Yeah. Because otherwise there would be always infinitely many arcs. I do allow myself to move my arcs up to homotopy to any place I wish. Yeah, that's okay.
Could you give an example of an internal arc?
Yes. Let's say here in the polygon, so this gamma here would be a boundary arc. But such a gamma here would be internal. So the actual diagonals are internal arcs, yeah? So is this internal arc gamma prime? Well, let's call the boundary arc somebody else. Let's call the boundary arc. This one is on the boundary, and let's call this one here gamma internal. Okay, that's good. So is the internal arc, is it up to homotopy? Is it a boundary arc? I mean, yes, I could push it to the boundary like so. Then you would get something like here. Yeah, I mean, there's a homotopy moving this to the boundary. But then I move to 1, 2, 3, 4 boundary arcs at the same time, and I said this is not allowed. The system of arcs that I consider, they intersect the boundary only on its endpoints. Yeah, I cannot in between go through boundary points. So this one is not homeotropic to this one in my setup. Yeah. Therefore, this is not a boundary arc, and therefore it is an internal arc. Now I destroyed everything. Good. Where's my polygon? I shouldn't do this. Yeah, that's good. So you see my internal arcs? kind of in the disk model, in the polygon model, the internal arcs are the diagonals, the actual diagonals, and the boundary arcs are the arcs which are actually on the boundary. 1, 2, 3, 4. That's good. Okay. Then I would say let's leave it for here. We have established the notion of arcs on a marked surface, and we continue from there tomorrow. From tomorrow we will study triangulations of surfaces. That's good.